I am Naman Munot and welcome to the School of Physics. So today we are going to begin heat capacity and kinetic theory of gases. What? Heat capacity and kinetic theory of gases. So let us write it down. Heat capacity. Heat capacity. Okay. Heat capacity. Now what is heat capacity? Heat capacity, as the name suggests, is the amount of heat that is required to raise the temperature of a system by 1 degree Celsius. Listen to it again. Heat capacity is the amount of heat required to increase the temperature of our system by 1 degree Celsius. So as we can write it down, say heat capacity is capital C is equal to the amount of heat required delta Q upon to raise the temperature of the system by 1 degree Celsius. So if the temperature delta T is 1 degree Celsius, then the amount of heat required will become heat capacity. So when delta T is equal to 1, the heat capacity is the amount of heat given. Okay, so you got the definition. Now we have some other definitions, that is molar heat capacity. So molar heat capacity is the amount of heat given to raise the temperature of 1 mole of substance by 1 degree Celsius. So we can write it down as molar heat capacity Cn, or say small cn, or we write it down as Cp and Cv. So molar heat capacity at constant temperature and molar heat capacity at constant pressure. Okay, so Cp is equal to C, that is the capital C, this is the small c, small cp is equal to capital C by n, or we can write it down as delta Q upon n delta T at constant pressure. Delta Q upon n delta T at constant pressure. Okay, similarly we can write as Cv. Cv is equal to C by N at constant volume is equal to delta Q by N delta T at constant volume. Okay, so this is Cp and this is Cv. Okay, so the next thing that we are going to write it, just hold on. Okay. The next thing that I am going to tell you is specific heat capacity. It is the amount of heat required to increase the temperature of 1 gram of substance by 1 degree Celsius. So specific heat capacity, we write it down as S is equal to the heat capacity upon the mass in grams. Heat capacity upon the mass in grams, or we can write it down it as delta Q upon M, that is M is the mass in grams, into delta T. So this is the specific heat capacity. Now we have a very interesting relation. That we use a lot of times in the whole of thermodynamics and heat related chapters, which is Cp minus Cv is equal to R constant R, which is 8.314. As you know, Cp minus Cv is equal to 8.314, that is R. Okay, and then there is this constant called adiabatic constant gamma, which is also written as Cp by Cv. Gamma is written as Cp by Cv. Now gamma has one more formula which takes us to the next part of the chapter, which is kinetic theory of gases. So gamma can also be written as so gamma is a very important thing, you'll see it a lot of times. So gamma can also be written as gamma. This formula is a very star formula. This will be used a lot of times. We'll give you direct answers. Gamma is equal to 1 plus 2 upon F. Gamma is equal to 1 plus 2 upon F, where F is the number of degrees of freedom. Okay, now degrees of freedom takes us to the next part of the chapter, which is kinetic theory of gases. Kinetic theory of gases. Kinetic theory of gases. Okay, so to begin with kinetic theory of gases, first I would like to ask you, what is the law of equipartition of energy? So the law of equipartition of energy says that with every degree of freedom F, there comes half kT energy, where this constant K is the constant we denote as R by N A. N is the mole number. So this is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. Okay, so this constant K is 1.38 into 10 to the power minus 23 joule per Kelvin, and with each degree of freedom we have half kT energy, which is called the law of equipartition of energy. Okay. Then I want to tell you about the mixture of gases. Okay, suppose we have a mixture of gases. So how will we calculate gamma for a mixture of gases? Okay, so for a mixture of gases, Cp, so suppose I have a lot of gases, gas 1 with moles N1, gas 2 with moles N2, gas 3 with moles N3, gas 4 with moles N4, and so on. And this gas has Cp1 and Cv1. Then this has Cp2, Cv2. This has Cp3, Cv3. Okay. So Cv net, okay, of the mixture of these gases. Suppose I mix all of these gases together. So the Cv net will be equal to N1 Cv1 plus N2 Cv2 and so on upon N1 plus N2 plus N3 and so on. Okay. Similarly, for Cp, we have Cp net is equal to N1 Cp1 plus N2 Cp2 and so on upon N1 plus N2 plus N3 and so on. Okay. Now gamma net will be equal to Cp by Cp net upon Cv net, as we have seen, Cp net upon Cv net, which is equal to N1 Cp1 plus N2 Cp2 and so on upon N1 Cv1 plus N2 Cv2 and so on. Okay, so this is for a mixture of gases. We can write it down, the gamma net formula. Okay, now I'll tell you Maxwell's distribution of energies. Okay, so Maxwell distribution of energy. So we're talking about we were talking about Maxwell distribution of velocities, but before that we're talking about degrees of freedom. Okay, so degree of freedom, it is different for monatomic gases, diatomic gases, linear, polyatomic gases, and polyatomic gases, linear. So first I'll write it down. Monatomic. So for monatomic, the degree of freedom is 3. For diatomic or polyatomic, linear. Mind this word, linear. Polyatomic, linear. Degree of freedom is 5. Then for monatomic, for diatomic, and then we also have for diatomic and polyatomic, non-linear. Okay, non-linear. For diatomic and polyatomic, non-linear, the degree of freedom is 6. Now this chart is going to be very important. First I'll tell you what the internal energy is. Okay, so the internal energy for n moles of gas is F by 2 nRT. So suppose n is 1, so the internal energy for a monatomic gas will be 3 by 2 RT. Okay, considering n is equal to 1. Just a second. Considering n equals to 1, we are having this as 3 by 2 RT. Okay, 3 by 2 RT. Then similarly this 5 by 2 RT. Then this is 6 by 2 yani 3 RT. Okay, then we have CV. Okay, so what is CV? CV is F equals to F by 2 N R. So suppose N is equal to 1, so we have 3 by 2 R, then we have 5 by 2 R, then we have 7 by 2 R. Then what is CP? As you know, CP minus CV is equal to R, so CP is equal to CV plus R. So this will be equals to 5 by 2 R, this is equals to 7 by 2 R, we are just adding R in CV, and this is equals to 9 by 2 R. Okay, now this very important formula that I told you, which is of gamma, so I'll write it down here. Gamma is equal to 1 plus 2 by F. Gamma is equal to 1 plus 2 by F. So in case of monoatomic gas, gamma is equal to 1 plus 2 by 3 is equal to 1.67. Then this is 1 plus 2 by 5, 1 plus 2 by 5, which is equals to 1.4. Okay, and this is 1 plus 2 by 6, which is 1 plus 1 by 3, which is equals to 1.33. Okay, so this chart, you can see, you can have a complete look of this chart. This is the most important chart and summarizes your kinetic theory of gases. So next we go to Maxwell's distribution of speed. What is the root mean square speed? What is the most probable speed? And then also what is the root mean square, most probable, and average. So this is the Maxwell's distribution of speeds. So for the particles, for the gas particles, if this is the number of moles, so the speeds go something like this. This is the velocity distribution. Okay, this place where n is maximum, that is most particles, will have velocity most probable speed. Now here we have somewhere V average, and this is velocity root mean square. Okay, so we need to remember the formulas because direct formulas will come. So we know that V RMS is greater than V average is greater than V most probable speed is greater than V most probable speed. So V RMS formula is under root 3 RT by M, under root 3 RT by M. This is greater than V average formula is under root 8 by pi. You just have to remember the constants. Here it was 3 in RMS, here it is under root 8 by pi RT by M, which is greater than most probable speed. It is under root 2 RT by M. Okay, this is the most probable speed. Now in terms of pressure, so whenever it is asked what is the pressure of the gas, okay, pressure of the gas, very simple formula, 1 by 3 into density, 1 by 3 into density of the gas into V RMS whole square. So this is the pressure of the gas, 1 by 3 into density into V RMS whole square. So guys, that was our kinetic theory of gases. I hope you enjoyed the chapter. Just keep on revising the formulas, very simple formulas. Thermodynamics is very easy. Heat related chapters in physics are very easy. All you need to do is understand the concept and revise the formulas. Please subscribe to my channel. Thank you for watching.